Thank you. Thank you, the organizers of QSQT 2025, and especially Professor Panigrahis for getting me into giving this talk. So, today I'll be talking about PT-symmetric quantum systems, some overview and uses. So, it will be a kind of a review, honestly speaking, of the recent advantages and recent work in PT-symmetric systems regarding quantum mechanics and quantum field theory and other aspects. So to begin with, I must say that I am not actually someone who works in discrete quantum systems or even quantum computation and related areas. So I worked in PT-symmetric systems, quantum systems earlier, but mostly continuous systems. So, but still, I would like to motivate people how these particular kind of systems contribute to different, appear in different areas of physics and contribute at different avenues in physics, essentially. So, to begin with, first I would like to just talk about our place where I work. So this place is called Nakhon Sawan, which is some 4 hours away from Bangkok towards to the north, and we are in a relatively scenic surrounding. It's a satellite campus of Mahidol University, and therein we have this Center for Theoretical Physics. And we are just into the 5th year of our existence. So we'd actually love to have more people coming in here and giving us the opportunity to expose our work. So yeah, regarding the talk, so the talk is now distributed mainly in 3 parts. So firstly, I'll talk about mostly the PT-symmetric structure, the basics, because some people may not be familiar with it. Then I would go to a particular kind of experimental setup, especially optical systems, where PT-symmetric systems were first realized. Then maybe more people will be interested in finite quantum systems, where these PT-symmetric ideas have been used, and especially its role in entanglement and decoherence and in other aspects. Then I'll try to give an overview on different areas where PT-symmetric theories are giving unique results, like field theory, condensed matter, and cosmology, and others. So first of all, the PT-symmetric structure. So PT means basically, P means parity and T means time reversal. So which is a very standard notion in basic physics. So PT-symmetric systems, if we talk about quantum systems, PT-symmetric systems are important when we talk about realistic systems where you have gain and loss. For example, if you have a complex Hamiltonian and you have corresponding eigenstates, obviously the energies are complex conjugate, complex, and because of that the imaginary part usually results into gain or loss of the system, depending on the sign of the energy, imaginary part of the energy. And that is kind of expected. But it so happens, if the system has parity and time reversal symmetry, although it is not Hermitian, as such that the eigenvalues are complex and the Hamiltonian is non-Hermitian, we can get real eigenvalues in certain situations, even if this just violates the Dirac-von Neumann interpretation of quantum mechanics. For example, a simple example is this complexified harmonic oscillator, and the carbonic. This system was known since many decades to have real spectra for certain values of the parameters. You can say mass or frequency, etc. For certain combinations, you end up with real energies, like standard harmonic oscillator energies. It was known earlier also, and there are many other physical systems also. So based on these ideas, in 1998, in a seminal paper by Bender and Botcher, they showed that actually for the real spectra, Hamiltonian strictly doesn't need to be Hermitian. It just needs to be invariant under combined operation of space reversal and time reversal. But when you talk about time reversal, we also include complex conjugation. That is actually the anti-unitary operation of time reversal operation, where the operator essentially affects parameters of the system if they have an imaginary part. So for specific interest, we usually focused on Hamiltonians, which are PT-symmetric but not Hermitian. Because if one checks all the Hermitian Hamiltonians that we know in all the physical systems, all of them by default mostly are PT-symmetric. But that is not an interesting case. Now, if we consider only PT-symmetric Hamiltonians, which are not Hermitian, for those systems, if we vary the system parameters for certain values of the parameters, what we can have only real eigenvalues. And for some other set of parameters, other values of those same parameters, we might have complex conjugate pairs of eigenvalues. And these two phases, where you have real and complex conjugate pairs of eigenvalues, are called symmetric and broken phase, respectively. What happens that in the broken phase, the complex conjugate energy eigenstates are related to each other through PT transformation, whereas in the symmetric phase, this eigenstate itself is PT invariant. So that means that although broken, there is a reminiscence of the PT symmetry of the Hamiltonian, where you have eigenstates are classified into complex conjugate pairs always. And essentially you can show that it actually results a spectral bifurcation, that if one tunes the parameters from, say, starting from the real spectra, the spectra gradually goes on changing a little bit, still stays real, and at a certain point the spectra just bifurcates into complex conjugate pairs for each real energy. So the point of this bifurcation is known as exceptional point, or rather points, because each real energy separates into one complex conjugate pair. And if one approaches from the broken side, where we have complex conjugate pairs, the complex conjugate pair eigenvalues, they just coalesce into these points. So the system is essentially losing degrees of freedom. Like the normal modes, number of normal modes actually decrease when you come from the broken sector towards the exceptional points. And they show many interesting results. But here the usual thing is that if the system is complex, how do we define norm? Because the Hamiltonian, which is not Hermitian, it is showing real eigenvalues. So the usual Dirac-von Neumann prescription of the vector space doesn't work. Rather, we need to redefine the scalar product itself, where the dual of the vector space is obtained through a combined combination of PT with another operator C. That gives a semi-positive definite inner product, which can be related to probability distribution. So this C operator is technically called charge conjugation, but this is not the physical charge conjugation operator that we have. It is just an operator which is necessary to define the inner product. It represents certain symmetry of the Hamiltonian, obviously, because the commutator vanishes, and this whole integration actually over the complex coordinate space has to be done on a well-defined contour, not over the whole complex space. And I would like to mention right now that this C operator is actually the difficult thing that somebody needs to construct for a PT-symmetric system, because the nature of this operator depends on the particular system. Okay, then what about the observables? Actually, for that, we should go to a more generalized construction, which includes PT-symmetric systems, which are known as pseudo-Hermitian systems. So these are systems which are not Hermitian, but they behave like Hermitian systems under certain conditions. So where the Hermitian conjugation is defined through a non-trivial operator, which is called the metric operator, here denoted as eta. So the inner product itself is defined in terms of this eta. You have to sandwich this eta operator between the states, and any expectation value or matrix element of any other operator has to be defined in addition with eta, this metric operator. So this is actually a general definition of scalar product or inner product in any vector space in general. So it so happens that for the Dirac-von Neumann vector space, we have eta to be the identity operator. So now, if we can construct an metric operator, what happens that we have a semi-positive definite norm, which will give stationary probability and orthonormal eigenstates with real spectra, and everything will pass through. So how to actually construct this metric operator is that if one notices that the PT operator itself kind of related to this metric operator through the definition of PT symmetry of the Hamiltonian, and from there up to a undetermined factor, this operator, the charge conjugation operator, can be represented as e to the power q into p, with p is the parity. So from that relation and from the definition of the metric operator, we just get the metric operator to be exponential minus q. And this q term, for continuous system at least, it's very complicated to obtain. There are perturbative techniques which are proposed, but there are difficulties depending on the parameter distribution or type of the system or the dimensionality of the system. There are many issues, but it so happens for finite dimensional systems, it is relatively easy. Now, if we look at the dynamics of such systems, usually the quantum systems which are PT symmetrics are given by potentials which are PT symmetric, but because we are talking about solvable systems and all, mostly these potentials are actually time independent. So what happens that the time reversal just means complex conjugation. We can practically talk about this if we are talking about the eigenbasis, definitely, because there is no effective time dependence. So what happens that if we want to construct something like a continuity equation, we can take complex conjugation as a substitute for time reversal. And if you do that from the Schrodinger equation, we can just construct this continuity equation where the conserved charge density, charge density, is basically a non-local quantity. So it depends on x as well as minus x. So already there is a non-local correlation in the system by construction. So similarly, one can define a conserved charge by volume integrating the charge density, and which is basically the expectation value of the parity operator. Now, considering the time evolution, one can actually see this charge conservation, and from this charge conservation, the equation boils down to this last equation where E minus E star into the inner product is 0. So if the energies are real, then the correlation itself or the inner product itself cannot be 0 in general. In the broken phase, correlation is identically 0, this particular correlation, but in the symmetric phase, it may not be 0, so it can exist. So what happens if we talk about such symmetric phases? Essentially, we can model them by a system where you have a localized potential. It may be complex if it is PT-symmetric, and two plane waves coming from both sides, or the time reverse version of the same, that two plane waves going out of the potential region. And these two are the only combinations in this one-dimensional simplified case which represents these parity inverse correlation. Basically, it gives non-zero correlation. So mind you, a single particle coming from the left, a plane wave, does not represent this parity defined correlation. You need two waves from both sides, either coming in or going out. And this was exactly obtained experimentally in optical systems in something called CP8, coherent perfect absorbers. So before going into that, just to mention that the symmetric phase, only the symmetric phase here has non-zero correlation. The broken phase will correspond to a current where the probability is not like stationary, or the inner conserved product is not stationary, and the eigenfunction is not PT-symmetric, and because of that the current doesn't vanish, so system can decay. And if you have this non-local correlation, you can have non-zero non-local effects. So the optical analog for such PT-symmetric systems actually comes from the realization that the Helmholtz equation itself for a one-directional waveguide can mimic the Schrodinger equation, where time is replaced by, say, z coordinate, and we have this kinetic energy part. Then we have the potential to be given by the refractive index. And in this case, for PT-symmetric representations, the refractive index is complex in general. Lambda naught is the wavelength of a particular wavelength of the light in vacuum, and N naught is the background refractive index in this case. So we have a notion of mass and etc. here. So what was observed in these systems when you look at a waveguide and pass through light, which has complex distribution of refractive index, the gain loss balance is broken for certain parameters. You can see those are the photos B and C, where the light distribution is asymmetric. But sometimes for certain parameters, certain values of the refractive index, which can be tuned physically, it has a nice circular, well-balanced distribution. So in the other model also, that in the symmetric phase, that we can have equal energy distribution in both gain and loss part, and intensity distribution. And for the broken part, either we have a gain channel activated or a loss channel activated. But more interestingly, if one sees the refraction and transmission coefficient, what happened that for certain values, the loss itself can become 0. And the transmission can become dominant. And that is effectively transparency. So this phenomenon is known as loss-induced optical transparency, which is a specific property of this PT-symmetric optical systems. Now, if somebody can construct this PT-symmetric profile with lasers coming from both sides, then what happens that the system can completely absorb the laser. So there will not be any outgoing signal. And that was proposed and also experimentally realized in certain kind of system like silica. And that was known as, that is called the coherent perfect absorber. And the time reversed version of that is that if we excite a system, just the two signals go out from both ends of this waveguide, and that is the CPA laser. And these systems were perfectly aligned to the conserved correlation. We just saw that it gives the boundary conditions which satisfy these systems. And more so in these systems, selective absorption happens. What happens that we can tune the parameters that some portion of the material will absorb the whole signal and there won't be any output, and some portions will have both absorption and transmission outputs, you can say. So that can be done also. So this works wonderfully for constructing switches and signal devices and detectors, etc. And there are multiple uses for these systems, although I'm not aware of the actual industrial use of these things as of now, but it holds potential in that case. So yeah, so I'll now go to the applications. So before that, if anybody has any questions, I'd be happy to address.
Yes. Yeah.
Yes, yes. There's in that RD is in some way related to time crystals. Uh, okay, honestly speaking, I am not aware of this, but regarding that time crystals, there could be because if a system has some time directional preference, it can be compensated by the parity structure of the system to obtain PT symmetry, but I'm not aware of actual use in time crystals of PT symmetry. Okay, is there anything else? Okay, so let me proceed. So now I'll just like to talk about finite quantum systems. So the simplest PT-symmetric model actually mostly people propose is this two-level Hamiltonian. One second. Oh, sorry. Okay. Yeah. This two-level Hamiltonian, where the parameter theta is usually called the PT-symmetric parameter. Or rather, you can see this potential is in general complex, and what happens that the parity operator for such two-level systems is just the first component of the parity, Pauli matrices, and time reversal is the identity operator and complex conjugation. So that is a preferred choice. We can take it. And if you look at the energies, clearly there is a square root term which has a minus sign. So there can be imaginary part also. So you have complex conjugate. So for certain values of S, R, and theta, we can have complex conjugate pairs of energies, otherwise real energies. So this is very simple in this case. So if you go to the symmetric phase where the square root is real, we have these eigenstates, and more importantly, for such systems, it is very easy to construct the charge conjugation operator. So this is one of the systems where we can actually very easily construct the charge conjugation operator exactly. And these eigenstates for the symmetric phase are eigenstates of charge conjugation also. So what happens that under the CPT conjugation, we can construct this dual space through CPT operation, and the inner product is totally fine. It can define probability, and what happens that these systems essentially violates Bell's inequality when they are considered explicitly, which was shown back in 2021. So it becomes an interesting study for quantum information also. So if we talk about the parity, these states are parity eigenstates also. That is one of the advantages of this system. And the whole argument that that there is a non-local conserved correlation that actually passes through. Now what happens that if you have this conserved non-local conserved charge, you can actually talk about entanglement. For that, we need a SU2 structure of the system. So one can define projection operators like these, and these projection operators can combine to give SU2 generators. So this is the spin of the system, quote unquote, that can be interpreted. And through these spin projections, one can construct the Bell operator in this way. And this Bell operator can have a well-defined expression in this PT-symmetric basis, but it follows, this expectations follows some constraints coming in from the charge conservation. Obviously, because it is true for PT preserved phase, because otherwise the charge conservation doesn't work physically, because the overlap vanishes itself, that we have seen already. So for this particular kind of PT symmetric potential, if in general if the interaction is PT symmetric, then then practically this charge conjugation operator to determine even for continuous analog for these systems is considerably hard. And I personally haven't seen anywhere where they have constructed a general charge conjugation operator for continuous systems. Even though you can construct these spin operators even for continuous systems. Okay. So people have studied recently open quantum systems which are PT symmetric. There, complete information retrieval is possible, but only in the symmetric phase where there is no loss. Okay, that makes sense. For that, the distinguishability parameter, that is the expression, it carries, distinguishability operator, you can say, it carries a parameter A, which actually is responsible for PT symmetric behavior, means PT symmetric transition from broken to symmetric phase, because it appears under a square root. And what happens that the broken phase, the distinguishability itself follows a power law decay, which was observed experimentally. Like the symmetric phase is represented if A lies between 0 and 1. And for that, if you notice, we have a periodic distinguishability. Otherwise, the distinguishability, the moment A approaches towards 1, towards the broken phase, it just decays very sharply. So this periodic behavior is something which is unique to PT symmetric systems in this regard, and that makes complete information retrieval possible. And what happens that interestingly for PT-symmetric systems, decoherence can get negated in due to PT-symmetry. So in particular, for spin boson systems, which has such kind of a Hamiltonian where the last term actually has a PT-symmetry breaking or restore parameter tau, this parameter actually can be varied to see that the decoherence itself is actually behaves differently in the symmetric and broken phase, and for that again there are peaks that appear for decoherence for certain value of this parameter theta. So there is one more ratio value parameter. So in the parameter range where the PT symmetry is preserved, decoherence is considerably high. So finally, regarding entanglement, same thing appears. There is a parameter, the complex parameter that actually governs the PT symmetric structure of these quantum systems. Uh, it it actually supports decoherence in the sense that in the XY model, it's a very simple structure. They have this angle parameter phi, which represents this PT symmetric transition. And the critical point is phi is equal to pi by 2, where even the behavior of teleportation fidelity is maximum. And you can see the behavior of the fidelity where there are lots of high peaks that appear periodically, and this periodic behavior again is a nature of PT symmetric system. Strongly in the symmetric phase they will appear for different values of other parameters. Okay, and what happens that the PT symmetric phase also supports robustness against thermal effects, and like loss of information is less in these cases, but again the periodic nature is prevail up to certain temperature. After that it decays. Yes.
The slides are not visible completely. It's partially visible.
Is it
Yeah.
now?
Yes, sir. It is good now.
Okay. Thank you. So, okay, one other interesting system is just I'd like to mention is called anti-PT symmetric systems. So these are just like PT symmetric system, just that the Hamiltonian itself anti-commutes with PT, and the energy eigenvalues in the symmetric phase are completely imaginary, and in the broken phase they are complex conjugate, unlike anything. So any anti-PT symmetric system is basically I times a PT symmetric Hamiltonian. So people have studied a 2-qubit system with anti-PT symmetric properties, and they also show entanglement. And there are some salient features that in the unbroken phase, the entanglement is periodic for if two systems are evolving identically, and it is aperiodic if they are evolving differently. Particular form of the Hamiltonians we can adjust with the parameters. So this gamma and Si are the parameters for I being 1 and 2 for two systems. Then at the exceptional point, what happens that the entanglement suddenly vanishes and suddenly it reappears also. There's a property, and if only one system is evolving under APT symmetric Hamiltonian, then only periodic behavior is observed. So what happens, this aperiodic behavior is a signature of that both the systems are evolving under APT symmetric evolution. So if they're left alone to behave on their own, they just behave periodically like any other PT-symmetric system. So it is kind of similar. But when they behave together under the same APT-symmetric evolution, then what happens that they develop certain kind of correlations, which gives aperiodic behavior of the entanglement. So which are fairly recent works actually. So okay, from now I'll go into some other areas of physics, some of which I am recently following, especially the field theory part, and some uses in condensed matter and other parts. So let's see. So what happens, there are some interesting features for PT-symmetric systems when we go to continuous fields. The earlier example, what Bender gave for PT-symmetric system, where there was an IX term, so in the potential, that got generalized into a non-covariant Lagrangian, where there is a parameter epsilon, which lies between 0 and 1. And why I'm saying non-covariant, because there is no time derivative in the Lagrangian for the field. So what happens that if this parameter is small, then one can do periodic expansion, because exactly solving such a Lagrangian is not essentially possible for arbitrary epsilon because of indefinite nonlinearity. So what happens that the perturbative energy shift is actually real if epsilon is very, very small than 1, and although there is an expansion in terms of I phi. So what happens when we expand the correlation functions, it can be seen also that 1 and 2 point functions are essentially functions of epsilon up to the first order, and also they depend on the Hermitian correlator. Basically, when you switch off this epsilon, you put epsilon is equal to 0, the correlator we get, 1 point correlator, is this delta naught, and all correlations can be expanded like that. And these systems in this symmetric phase show real spectra, and the correlators can be determined properly, and Feynman diagrams can be calculated also. Then, if we talk about a covariant model, so there is a British group under Alexander et al. They did extensive work in last 5, 6, 7 years, and they showed that we can construct a covariant theory where we have to construct, at least in the scalar case, we have to consider 2-component scalar and a mass matrix where there is a non-Hermitian nature because of the structure of the mass matrix M square. So the non-diagonal element, this mu square in the mass matrix, that actually contributes to this non-Hermitian nature. Again, parity is just the third Pauli matrix in this system, and time reversal is just complex conjugation in this two-level representation of the system. So under that, because of the structure, phi 1 is a scalar, but phi 2 is a pseudo scalar. So that essentially explains that the system has a gain loss kind of a property. This is kind of a gain loss analog. So one can define a sink and source that will get visible very soon. So what happens that the critical behavior of this system arises when 2 mu square is equal to the difference of the modulus of the difference of the squares of the individual masses m1 and m2, the normal Hermitian masses, and also the charge conjugation is actually equal to the parity, which is reflected through the result that the physical observables of the system does not depend on the sign of this mu square term, the Hermitianity breaking term. So one can construct this equation motion of this system. So there are two fields, two equations of motion, but the striking feature is that these equations of motions are not simultaneously valid. So either one can have one or the other, and which is totally distinct from the Hermitian case, what we are usually familiar with. So what implication it does, that if you just see the variation of the Lagrangian under the arbitrary variation of the fields, what happens that the total derivative contribution that come along with the Lagrangian, that if that is non-trivial, we say there is a conserved current. But because the equation of motions are non-zero, the Euler-Lagrange factors corresponding to each field, they don't disappear together. So because of that, if you need the current to be conserved, the total derivative has to be zero on its own, and the variation of the Lagrangian has to be non-zero, so that the non-trivial portion coming from non-vanishing of one Euler Lagrangian factor is cancelled out. So it doesn't look similar to what we usually know, that the Lagrangian, the total variation of the Lagrangian is equal to a total derivative, and we say, okay, if there are well-defined boundary conditions, the total derivative vanishes and the current is conserved. But here it is not the case. The Lagrangian actually locally changes. So what happens if you have the interesting case when you have mu to be non-zero, means the system is PT-symmetric. So only a particular combination of these currents, these two currents corresponding to a particular U1 symmetry, where phi1 and phi2 actually change under opposite charge alpha, that current is conserved. So this is a kind of reminiscent of the chiral current that is conserved. But this this U1 transformation, that phi1 and phi2 varies differently in terms of the sign of the parameter. That actually shows that these two fields have opposite charges. So that means you can interpret it in terms of particle antiparticle kind of things. So it can be interpreted in terms of gain and loss also. So this structure is very general in all the field theoretical models, that the Lagrangian is not invariant under a particular transformation, but the current, some current is conserved, which kind of violates Noether theorem also. But this is, one can consider it to be a generalized Noether theorem for these systems. So finally, we can have Fermi analog, again the same property, that the Lagrangian doesn't, the variation of Lagrangian doesn't vanish under a particular transformation. And in particular for gauge interaction, the conserved current is somehow looks like the chiral current that we have, but the chiral parameter, chiral term is controlled by the ratio of mu divided by m, where mu is the PT-symmetric mass contribution for the Dirac-Lagrangian. And because of that, what happens that there is a one particular chiral combination is conserved, so the other one is not. So there is a left-right asymmetry comes in for the system, depending on the ratio of mu and m. And the exceptional point is when mu modulus is equal to m, and what happens, one current is suppressed there, some linear combination maybe. So the number of chiral mode decreases, and what happens, the gauge invariance of the whole Lagrangian is restored in the exceptional point. So it behaves like a Hermitian system, but only at the exceptional point. So there can be a generalization with QED also. I don't want to go that much. The charges needs to be adjusted. So this gamma 5 term, the Dirac matrix gamma 5, that the chirality matrix, that controls PT symmetry. So the parameters here, now there are two parameters which control PT symmetry, this GA and mu. And under these particular gauge transformation of uh, the system is no longer gauge invariant, and but there is a conserved current, one can see again like that. And what happens, only under critical point the gauge invariance is restored again. And one can extend these kind of terms with some 5-4 interaction, which will give a Goldstone mode with proper parameter adjustment. And this Goldstone or zero mode that appears, although again the Lagrangian actually changes under these transformations. So it again it's counterintuitive to what Goldstone theorem says us. But again, the Goldstone theorem is restored that there is a symmetry when we go to the critical point. So the same property is seen for Higgs case when we bring in gauge fields with interaction, and there is a non-abelian generation also. But the non-abelian generation is a bit complicated. The degree of freedom reduction and coming into the exceptional point is essentially possibly unstable. People have studied supersymmetric theories with PT-symmetric potentials also, and but there are problems like there is no Majorana sector, and the supercurrent is actually ambiguous. So lots of other treatments has been done, but this is still at the early stage of formulation of a PT-symmetric system. So these systems are actually realized in physics, like these complex systems, and tuning the parameters. One can have field theoretic PT-symmetric systems, but experimental detection of these this particular novel phenomena regarding PT-symmetric field theoretic systems have not been done yet. But the formulation is very much recent in that regard. So if I go to now condensed matter systems, and we see it is like practically more tractable, and what people see are that there are novel topological phases which are actually stable in PT-symmetric systems, although the spectra is complex. Particularly this SSH or Schrieffer-Heeger model, where the third term you can see there is a I factor. So this G is the PT-symmetry parameter, and when what happens that these systems show some interesting topological behaviors, like there are zero modes there, which are also observed in the real systems. But the chiral properties of this system, where we observe edge modes, they are very much directly linked to the exceptional points in the bulk. And also there are topological superconducting effects with Majorana modes, where we see some boundary modes which have superconducting behavior. As for the dispersion has a potential complex behavior because the square root contains a minus sign. And because of that, what happens that the Dirac point for such systems, when we consider about 1 or 2-dimensional systems, the point itself opens up into a ring or multiple lines, and that essentially talks about a distinct topological change, and that is not seen in real systems. So maybe experimentally people would be able to detect it. But constructing such systems is again maybe a challenge experimentally. So finally, also like PT-symmetric Kitaev-Majorana chains with topological superconductivity has been observed. Again, where the Hamiltonian itself is given with a term which is the last term, uh, which the complex term, which basically considers the edge excitations. So also in cold atoms, basically lithium-6 systems, ultra-cold atoms, people have observed quantum chaos, and this kind of systems actually are important, and they have in general SYK or Sachdev E type kind of structure, and it has implications in random matrix Hamiltonians also. People have classified the symmetry, larger symmetry class of such systems, and they look considerably different from real systems. So, and also in cosmological systems, one can add the matter part to be a complex scalar kind of structure, where you have an imaginary part, and this imaginary part actually can mimic the dark energy. And one does a dynamical system analysis, the dynamics is stable, which is very important, because usually dark energy models may not have stable dynamics in most of the cases. Again, it's a multiple scalar model, which is known to give stable structures in cosmology. But they don't lead to big rip. They kind of give a well-behaved universe, even in distant future, which is actually good for the future of the universe. The present quantum model with the Hamiltonian, Hamiltonian or Hermitian action doesn't have this property, this stability. Also, Hawking radiation can be treated. It is shown that the Hawking radiation is equivalent to a quantum tunneling across the event horizon. So it's equivalent to a two-level system, and it has a very simple interpretation. So finally, actually, what it shows that an infalling observer near the black hole experience a tilted light cone. Like the light cone is tilted, and the tilting is exactly because of this kappa parameter for this model Hamiltonian. And this kappa parameter is responsible for that tilting. So it can have nice tunnelings, which result to Hawking radiations, which is very much allowed, and the parameter itself governs the metric directly, and people can construct, given the symmetry, the dynamical implication of this parameter, and which gives extra stability to the system. So yeah, I'd just like to conclude. So what I just want to convey that PT-symmetric systems are actually physical as far as optical systems is concerned, and two-level systems are have been realized in quantum mechanically. But for continuous system, it is still a challenge to basically, because of the norm operator, that it can be a non-trivial structure. But these use of such systems, in at least in classical analogs, is very much practical, because they can result into very effective quantum switches. And also regarding foundational quantum phenomena like teleportation and quantum communication, it can be of good use because of the unique properties of PT-symmetric systems. And it also has formulational interest, because field theoretic systems, which are PT-symmetric, are very much useful for us, because of two reasons. It gives us some generalizations of conservation laws regarding the invariance of the Lagrangian and all. And secondly, the norm issue actually does not appear in field theoretical systems, because this norm operator does not affect the vacuum. So vacuum is invariant under the norm operator, so we can altogether forget the norm operator in this case. So field theoretic system regarding the unitarity structure is easy if the system is PT-symmetric. But then again, the physical realization of the results may be problematic. Okay, so I stop here and thank you for listening to me. So any comment?
Nice presentation, which extends not only from the basics of this PT-symmetric quantum system and extends up to the applications. I think really it will be helpful for all those who are present over here. Okay, so now it is open for discussion. Any questions?
I can already see a question in the comments. So they want me to go to the honeycomb lattice symmetry part. Okay, let me just go. Second, maybe here. Yes. So here that the question was. Let me again please go back. Question says that could you please can you? Okay, he wants to a re-explanation. So what happens that that the topological phase itself is actually stable even if you have complex vector. That means that okay, the PT symmetry is working and there is there is no loss decay if we have a topological phase. Like a topological phase in the sense that what we have, whatever topological phase we have in the Hermitian counterpart, if there is similar kind of topological phases also, or maybe something different. But in the symmetric phase, that phase is stable. That has been observed. So particular example in the SSS model, they have seen that. So they have seen topological zero modes and chiral topological edge modes in honeycomb lattice, which are stable for certain parameter values, which is interpreted as the PT symmetric preserve phase, definitely in terms of energy, and they are linked to exceptional points in the bulk. The point is that if you arrive at the exceptional point in the bulk Hamiltonian, that we can say in the broken phase, the energy itself becomes real suddenly for certain parameter values. So if that happens, then in the boundary, people see chiral topological edge modes, and that is seen in honeycomb lattice. So the honeycomb interaction, if you consider the geometry, this given Hamiltonian can be realized in honeycomb lattice, and Majorana modes are observed in topological superconductors. So I don't have the much detail right now because okay, this was a short overview of the area. But the important point is that for such systems, especially okay, two-dimensional system honeycomb lattice, if we consider, we know the energy there is a gap, and the gap, if you can if you have this gapless limit, the dispersions, they meet at the Dirac point, two cones merge, so this E plus minus kind of thing. But what happens, because we have this G factor, which is the PT symmetric factor, it makes this energy complex in general, and because of that we don't have a Dirac point anymore. That Dirac point can form complicated structures, can open up into complicated structures like ring and multiple lines. And what happens, that happens when we pass through exceptional points, that if we are coming with a Dirac point, maybe it will open up into rings or lines and vice versa. So I hope that explains.